We've been using the calculus to draw graphs, but where it's very useful, of course, is to solve practical problems. So maximum and minimum problems, obviously they're going to be word problems, but the sorts of things we're looking out for. So we're going to have a question, obviously, but we want to reduce it down to a set of equations. So instead of all being words, we want to turn it into maths, turn it into equations. Usually we'll end up with just two we're going to need. Now, what are we looking for? They're maximum and minimum problems, also sometimes called optimisation problems. And so you try and find the maximum of something or the minimum of something. So you read through the question and see what it is that you're trying to maximise or minimise and try and come up with an equation for that. The other one will be some information in there that will link the problem together. They might tell you the amount of material that you have to make something with or something like that. So that's the other equation usually. So then what we do is rewrite the equation that we are trying to minimise or maximise, so it's only got one variable in it. Then that way we can start using calculus, because we can say, oh, well, how does A changes, B changes, that sort of thing. So here's a classic example. I'm sure you've experienced this problem yourself. You've got a rope 36 metres in length, and you want to cut it into two pieces. Now the first piece of rope, we're going to make a square. And the second one is going to be a rectangle, but one of the sides of the rectangle is going to be the same as the length of the square. Sounding familiar? As I say, I'm sure you've done it many times. We want to find how big to make that square so that the sum of the two areas will be maximised. We want to get the biggest area possible. All right, I like to draw diagrams up to get a feel for what I'm doing. So there's my two objects. One's a square, one's a rectangle that I've made out of a piece of rope. Let's give it some pronumerals. Creatively, I'll call the length of the side of the square S for square. All right, my rectangle then, we know one of the sides is also S, and the other one I've called R for rectangle. We want a formula. We're trying to maximise the area. So the area of those two shapes would be S squared plus RS, but at this stage it's in terms of two variables there. I'm trying to get it down to one. So the other thing is a piece of information being given to me. The rope is 36 metres long. So in other words, the perimeter, because we've used all the rope, the perimeter of these two shapes will be 36. There's my second one. Now it's up to me which one I make the subject. I can make R or S the subject, substitute it into the first one. My choice. But I want to make life easy for myself, and I think it's going to be a lot easier to substitute R into the first one than it is to substitute S into the first one. So I'm going to make R the subject, and we get 18 minus 3S, sub it into the area formula, and there we go. Oh, well, let's tidy it up. Okay, 18S minus 2S squared. Now this actually gives us a couple of things we could use here. I'm going to use the calculus because, of course, the example. But if you look at it, we've actually got a quadratic. If you were going to draw area versus the side length, you'd have your parabola. And because we're trying to find the maximum area, I just got to find the A value of the vertex of the parabola, and that would solve the problem. So I could do minus the discriminant over 4A if I wanted to. But this is an example of using calculus, so I'm going to go that way. A is that. So differentiate it once. dA ds, 18 minus 4s. I'll differentiate it twice because we want to prove it's a maximum or a minimum. Stationary points occur. So again, still set up the problem exactly the same as if we're drawing a graph. The advantage of the calculus is, whilst I said it's going to be a parabola, we don't actually have to draw the graph because we can use the calculus to find the information that we need. Solve that. S is 9 on 2. And when we sub that into the second derivative, it's negative 4. Well, it's negative 4 everywhere, which is less than 0. So yes, the side length of the square is, and notice I didn't write 9 on 2. I mean, I could have. Kind of made more sense to say 4.5 metres, because you're talking about a shape and how long it is. You're not going to say, oh, it's 9 on 2 metres long. You say, oh, it's 4.5 metres long. Then the area is a maximum. Notice that solves the problem. Make sure you read the question and you're not doing extra work that you don't have to do. It's not actually asking what is the area. It's just simply saying what is the side length. 4.5 metres. Interesting thing though, is if you go back to our formulas that we had, have a look what that means for the rectangle. Remember, the length of the rectangle will be 18 minus 3s. We just said S was 9 on 2. Substitute that in, what's the length of the rectangle? 9 on 2. The rectangle actually turns out to be a square as well. This happens a lot in optimisation problems, where the biggest area, things like that, the perfect shape creates it. So the perfect rectangle being a square, things like that. Unfortunately, you can't just quote that though. You've got to prove it. All right, let's do another one. An open cylindrical bucket is made to hold the largest volume of liquid. Wow, it's lucky it's open then, because otherwise the answer would be 0. Because if it wasn't open, you couldn't get any liquid into the bucket. So the maximum it would hold would be 0. All right, so we have an open cylindrical bucket. The surface area, oh, how fortunate we were able to measure it that accurate, is 12 pi units squared. So we have 12 pi units squared of material. And we're going to make a bucket. And we want to find the height, the radius, and the volume. So there's a few things we've got to find here. Let's draw my bucket. There it is. Yes, it's not one of those buckets that are tapered in nicely. It's a nice, straight, cylindrical bucket. You know, maths in the real world. The other thing we're assuming here is we can use every piece of material to make this. There's no wastage whatsoever. Amazingly, we were going to be able to cut a circle out for the base and all that, and we'll use every bit. Reality is there's wastage. When you look at optimisation problems like this in uni, you have to take into account all those sorts of things as well. You take into account wastage and all that. We're looking at very simplified problems. Volume is what we're trying to maximise. Pi r squared h, of course, for volume, you will recall. Information, surface area of the bucket. Surface area of a cylinder. Who remembers surface area? No cheating and looking at the sheet. Who remembers surface area of a cylinder? Hang on, I'm hearing bits and pieces. What we got? Ah, very good. I was wondering if anyone was going to, out of habit, say 2 pi r squared. But it's an open bucket, so you don't have a circle on top. So it's only pi r squared for this one. So 12 pi is pi r squared plus 2 pi r h would be the curved surface area. That's what we call it, isn't it? The curved part. I can either make r or h the subject. Again, let's make life easier for ourselves. It seems to be more logical to make h the subject of the second one. 12 minus r squared over 2r. Substitute it into the volume formula and tidy that up. There's our formula for the volume in terms of the radius. So now we can do it. There's v. To v dr, differentiate it once. Let's find the second derivative, minus 3 pi r. Stationary points will occur when, in this case, the v dr is equal to 0. And we get two possibilities to check. Either r is plus 2 or minus 2. One of those we would assume is the maximum, the other might be a minimum. But one is certainly logical to test before the other. Which one do we test first? Why? Yeah, you're not going to get a negative radius. So it seems logical to test the positive number first. So when we sub in r equals 2, we get minus 6 pi, which is a negative number. So yep, when the radius is 2, volume is a maximum, but remember this one asks for some more information. Okay. We ended up with a formula for h. Remember when we rearranged the equation? Substitute into that. Oh, look at that, 2. There's that perfection happening again. What a weird bucket. The radius is the same as the height. If you think about it, that means the diameter is twice the height. Very strange bucket. Volume, sub into that one, we get 8 pi. So there's our answer. The maximum volume is 8 pi units cubed, and that happens when both the radius and the height are 2 units. So 4H and 4I are on all those sorts of problems, maximisation, minimisation problems.